So hi everyone, and hi everyone at home. They hear me, right? Okay, perfect. So as Francisco said, I'll talk about the Aldous-Lyons conjecture today. And are most people here like from quantum information or from math? Like maybe quantum information people raise their hands. Okay, and the math. Okay, mostly quantum information. So I'll say that this is kind of a mixed talk. I was asked whether it's a math talk or a CS talk. So it's kind of a mixture, and you will see that beginning will be very like things that for mathematicians are kind of standard, most of them, but for people from CS are less standard. And at some point it will be reversed, okay? But then the end we will see kind of nice results and everything will come together. So this is a joint work, so I wrote, this is a joint work with Louis Bowen, Alex Lubotsky, and Thomas Vedek. And the plan is to first just describe and to motivate this conjecture, the Aldous-Lyons conjecture. Okay, so that would be the first part. There won't be too much motivation. It will be really like one slide of motivation. I'll mainly like just define it to you. Then I'm going to define subgroup tests, which are, you should think of them as our analog of non-local games. So these are some combinatorial objects that define an interactive proof system, and I'll explain exactly how. And at the end, I'll relate the two, and this relation will resolve the Aldous-Lyons conjecture. Okay, so let's just start, and as I said, I'm going to start very basic. So I have a finite set, which will be my alphabet, and I denote it by S. And just as a running example, let's have A and B as our alphabet. Then I can define the free monoid over this alphabet, which is just the collection of all words over this alphabet. So ID is just the empty word. That's always a word for me. ABA, BB, and so on. And when I have two words, I can concatenate them. That's just a notion of a product over the free monoid. So for example, ABA concatenated with BB is ABA, BB. And this gives us an associative and an identity element is the empty word. So we have a monoid, as I said. But the problem with the free monoid is that it doesn't have inverses. I'm a group theorist, and I want something to be a group. So what do? You just define another copy of your alphabet. You call it the anti-alphabet, in this case, anti-S. And you just ask for whenever a letter and its anti-letter meet, they annihilate each other, right? Like a positron and an electron. And if you take the free monoid over the alphabet and the anti-alphabet, and you define this relation of annihilation between letters and anti-letters, you get the free group with basis S. Now, the free group is very nice. It has several nice properties. The first property that I want to talk about is its universal property. So free groups behave like vector spaces. Whenever you have a basis and you send it somewhere, you can extend it to a linear map from the vector space, right? So here we have the same deal. Whenever you send your generating set to some group gamma, it extends naturally to a homomorphism from the free group to this group gamma. And as an immediate corollary, whenever you have a finitely generated group gamma, it is the quotient of the free group. Okay, so there is an epimorphism. Maybe I'll take this thing. Okay. There is an epimorphism, an onto homomorphism from the free group to this group gamma, and it always has a kernel for this map, and this kernel is also always a normal subgroup of the free group. And as I said, this is very basic, but you will see later that this picture is important for us. Now, another way of viewing the free group is as the fundamental group of a very nice space. Okay, so what is the fundamental group? It's all closed paths that start and end at a given fixed vertex up to homotopy. And if you take this specific graph, so it has a single vertex and two edges, and I labeled the edges and also gave them orientation. You don't need to do that to define the fundamental group. It's just easier to relate to the free group that way. And then you can see that every closed path is essentially a word either in AB or reversed AB, right? There's a difference between going with the arrow or against the arrow. And thus, closed paths that start and end at this vertex are exactly words in A, B, A inverse, and B inverse, and saying up to homotopy exactly allows me to annihilate A and A inverse and B inverse whenever they come immediately one after the other. Great. So this is the topological or combinatorial viewpoint. And once you have a group, specifically for the free group, it's easiest to show. You have a natural topology on subsets, right? The Tikhonov topology, and this gives you a natural topology on subgroups. But at least in the case of the free group, there's a very straightforward way of viewing this topology, via a very nice metric. So if you have two subgroups, H1 and H2, subgroups of the free group, you can define a distance between them to be 2 to the minus r. And now I'll define what r is. If H1 and H2 are different subgroups, the symmetric difference has at least one element in it, right? This element is just a word in the alphabet and the anti-alphabet. You just ask what is the length of this word, and you take the shortest one. So out of the symmetric difference, out of the words that are in H1 and not in H2 or vice versa, just take the shortest one. This is r, and the distance is 2 to the minus r. This essentially asks you, in the Cayley graph of the free group, what is the smallest ball where you see actually the difference between H1 and H2? That's this distance. And this is my weird notation. This is not 5, 4, 6, but sub, okay, S-U-B, in like my weird font. So these are the subgroups of the free groups. And using this metric, as I said, this is just the Tikhonov topology. This is a compact metric space, okay? And again, it's not really important. Like those of you who don't remember what compact in this context mean, it doesn't really matter. It just matters that the next definitions are well defined, and this is a compact metric space, okay? Now, again, like those of you who studied the algebraic topology know that whenever you have a space, and you look at the fundamental group of it, and we remember this is the space for which the fundamental group is the free group, there is a correspondence between subgroups of the fundamental group and covering spaces, okay? So you can see here, what does it mean for it to be a covering space? In the case of graphs, it's very simple. So the covering space of a graph is always a graph itself. And you can see that above every vertex, there are exactly the same number of vertices. Above every edge, there is exactly the same number of edges, and the same for here. And the number of outgoing purple edges and the number of outgoing orange and the ingoing purple and ingoing orange are the same for all vertices. That's essentially like the combinatorial way of defining a covering space, but there is clearly a topological, like something that only see continuous maps. But in this case, that's all you need to define a covering space. And for example, you can see that this is another graph. You can look which words start and end, for example, in this pink vertex, right? So for example, A starts and ends in this pink vertex, but B doesn't. So A is in the subgroup defined by this covering space, and B is not. Now you can watch that the specific subgroup depends on the base point. So if instead of taking this pink vertex as a base point, I'll take this blue vertex as a base point, A will not be in the subgroup, right? Because A will move you to another vertex. So recall the fundamental group was all closed paths. You need to start and end at the same vertex, okay? So we see that subgroups depend both on the covering space and on the specific base point they chose for it. That's important. Now, the same thing can be viewed completely combinatorially here. Okay, so let me just explain it here. So if you have a function, we recall that if you have a function from the generating set to permutations, okay, acting on some space, it extends to a homomorphism from the free group. We said it in the universal property. And this just induces an action of the free group on this set omega. Okay, so instead of viewing something as a covering, I'm going to view it as related to actions. And whenever you have a group acting on a space, you can ask what is the stabilizer of a vertex. That's just all group elements that send this vertex to itself. And this is always a subgroup of the free group. And you can see that the association here is that if you send A to the permutation that swaps 2 and 3, and B to the permutation that swaps 1 and 2, and you just enumerate the vertices here as 1, 2, and 3, you will see that the stabilizer of 1 is exactly the fundamental group of this covering. And that always happens. Like whenever you have this action, you have this graph. And this is usually called the Schreier graph of this action. So you can always recover a covering space using the Schreier graph. And this is good for us. Now, you should ask, okay, is this omega finite or infinite? It can be infinite. For example, the trivial subgroup, the one that only contains the identity, the associated covering space is the 2S regular tree. Okay, so in this case, the 4 regular tree will be the covering space, which is associated with the identity group. Okay? So omega can be infinite in this setup. Great. Another definition that all of us know, okay, so if you have a subgroup and you have an element, you can conjugate it. And this defines an action of the free group on its subgroups, right? Like you just conjugate the subgroups. And my claim is just that this is a continuous action, okay, because we have a topology on the subgroups. And a subgroup is called normal if it's conjugation invariant. So no matter which element you try to conjugate it by, it remains the same. Great. Up until now, it was really like a brief recollection of algebraic topology and like basic things that you see there. This is something that even mathematicians don't always encounter. So in some sense, from here, new material appears. So what is a random subgroup? So beforehand, we have everything was deterministic. Now I want to define some sampling mechanism. So a random subgroup is just a probability distribution over the subgroups. Like it's the most natural thing you can think about in this case. But when I hear like Borel probability distributions, I usually get nervous. So let's just have some visual aid that will allow us to think about these things. So these are just black boxes with buttons on top that whenever you push the button, you get as output a subgroup, and the probability that you get the subgroup is exactly the distribution. That would be my visual aid, and it will be a very helpful visual aid. Now, this space of probability distributions over subgroups, so all random subgroups, also have a very nice topology. This is called the weak star topology. And at least in this case, there's a very straightforward, easy way of defining it. So let's see that we understand it. So a sequence of these black boxes, yes?
Sorry, I just wanted to verify. So
Yes, sure.
for our case, subgroups, this is always a discrete probability measure we would obtain, right?
What do you mean discrete probability distribution? Like this is a topological space. These are Borel distributions over the space. It was important actually that this is a compact space.
But I mean typically like in, you know, if you talk about a discrete probability distribution, it means that you sort of have like you have a countable number of you assign kind of a probability mass to each individual point.
If it was over subsets, clearly you don't have a countable number of subsets, right?
Yeah.
So, and this is also a compact metric space. And are there countably many subgroups of the free group?
I'm not sure about that.
Yeah, that's a good question. Like I don't have that on top of my head. I think not, but I'm not sure.
Okay, but so this would have to be in something that's by like a density function rather than just like a probability mass function.
Yeah, I'm not so. This space is probably kind of weird.
Yeah.
Okay, so we will see in a moment that we will actually restrict ourselves to even a smaller space.
Yeah.
And this smaller space is so weird that some decision problems are undecidable on it. Okay, so like you should think like, are you from quantum or from math? Like, do you know local games?
Science.
What?
Or from computer science, but anyway.
Yeah, so for example, like if you know quantum correlations and quantum commuting correlations and stuff like that, these are like, you can think of it something like non-signaling or something like that. This is like a big space which is kind of complicated, and you don't try to like automatically think that you understand everything about it. It has atom measures, like there are atomic measures there.
Yeah.
We will see in a moment. For example, actually for every subgroup, you can define just at this point,
Sure.
But we will see in a moment that it will become even more complicated. Okay, perfect. But let's focus on the topology on this space, the probability distribution over the subgroups. If I have a collection of random subgroups, a sequence of random subgroups, I say that it converges to like the limit pi, if and only if, and this is just the definition of this, for any finite set from the free group, you can define the following sampling mechanism. So you can take your random subgroup and intersect it with a finite set. What does it mean? So you just sample from your distribution, you get a subgroup, and you intersect it with K. Now, what did you get? You got a subset of K. K was finite, so the amount of possible outcomes here is finite. So pi end intersection K is just a probability distribution over a finite space. So this is just a vector of numbers between 0 and 1. We understand what does it mean for a vector of numbers between 0 and 1 to converge to another vector of numbers between 0 and 1. So if this condition is satisfied for every finite K, we say that this probability distribution converges in the weak star sense to this distribution. Okay, so that's my definition of what does it mean to converge in the space of probability distributions. Any questions about that? Okay, great. Now, similar to intersection, I also can conjugate probability distributions, right? Like I first sample the subgroup, and then I just conjugate by this fixed element that I wrote there, W acting on pi, and I get the conjugate of whatever I sampled beforehand. And that's another probability distribution over the subgroups, right? Potentially a different one. Clearly the mechanism is different, but I can still say that when W acts on pi, you get the same thing. What do I mean by that? Not that if you sample according to this sampling scheme, you get the same thing. That's not true. You get the conjugate, but just the distributions are the same, right? We don't think really about the sampling mechanism. We think about the distributions. So we will say that a random subgroup is an invariant random subgroup if it is conjugation invariant for every element of the free group. So that's just the random subgroup analog of being a normal subgroup. So, and actually the first example of an invariant random subgroup is just normal subgroups. So instead of giving me a random subgroup, just give me a black box that always outputs the same normal subgroup, right? That's a probability distribution, a Dirac measure, right? Like just everything, it will always give me the same thing. And it is conjugation invariant just because the normal subgroup itself, if this was a normal subgroup, that would be the same normal subgroup, right? That's the point. Great, a slightly more general situation is when, okay, you have your subgroup H, okay, maybe I'll write it here. Nice. You have your subgroup H, and you look at all conjugates. And this is a finite set. A priori, if you don't know anything about the subgroup, that can be infinite, or that can be finite. If this is finite, you can just take the uniform distribution over the set, and it will be conjugation invariant, because what the conjugation will do, it will just permute this set, but the uniform measure is invariant under any permutation, right? So a uniform distribution over the conjugation orbit of a single subgroup with a finite conjugation orbit is an invariant random subgroup. Okay, great. Now I'm going to define the most important class of invariant random subgroups for me. So I'm just giving you a way of generating lots of invariant random subgroups, which have potentially interesting properties. Okay, so this is the finely described IRSs. Okay. Now, again, I'm going to give you both the topological viewpoint and the combinatorial viewpoint. Okay. So topologically, you take a finite covering space. That's very important. Okay. So here I have a finite covering space. It has index 5. So you see the covering index is 5. It's not necessarily connected, and that's important for me, that I allow you to use disconnected covering spaces. Now, nothing is random about this, but recall that we said that the subgroup is determined according to the base point as well, right? So we have 5 possible base points, just choose one uniformly. Okay, so the IRS will be, the invariant random subgroup will be, give me with probability 1/5 the fundamental group of this covering space with respect to this point, this point, this point, and the other 2 points. And you can check that you will get the same subgroup here and here. Okay, so with probability 2/5, this subgroup will be the output. And with probability 1/5, you will get either one of these three subgroups, which are different from one another. That's an exercise if you want to check later. And so this already shows you that you don't necessarily get a uniform measure over subgroups. You get something a bit more rich, right? And a way of viewing the same thing, okay, is through the Schreier graphs. So again, now you have an action of the free group. You can just take a function from your generating set to the permutations over a finite set. Now it's just a finite set of elements, and you define a permutation, like S many permutations on them. You uniformly choose an element of this finite set, and you give me the stabilizer. And we define the stabilizer beforehand. Okay. So that's a finitely described IRS. And I just denote, so beforehand I denoted the IRSs of the free group without this finitely described, where all IRSs with this finitely described is the finitely described IRSs. And I want us to notice something. Okay, so this is not everything. Like not every IRS is a finitely described IRS. The easiest way to see that is that you always get a push forward of a uniform distribution over a finite set. So it always, for example, will be weighted on rational numbers. The weights, the probability of getting a subgroup is always rational, right? So if you take the closure, you can get actually also real weights for the subgroups. So you do get bigger things here, but that's the boring example. I claim that even if you take convex combinations of finitely described IRSs, so I allow you to put in like any real convex combinations of the finitely described IRSs, still you don't get everything. For example, I claim, okay, so maybe I'll write it here, and that's again an exercise that I think if you really want to feel what happens here, it's a good exercise. So you can take the free group acting on two elements, like with the basis 2. You can project it on the integers squared. Okay, and there will be some normal subgroup here, right? So you just can take the Dirac measure over this subgroup. So the random subgroup that always outputs this normal, this specific normal subgroup, like the kernel of this map. And I claim that this is in the closure of the finitely described IRSs, but it's not in the convex combinations of the finitely described IRSs. Okay. So this set, the fact that you take the closure, remember we have some topology here, we have this weak star topology, we can get like sequences of finitely described IRSs that converge to something bigger. So this is a bigger set, a strictly bigger set. These are the cosophic IRSs, and this is contained in all IRSs. Okay, so yeah.
Sorry, I'm a bit confused as to how this gives us a random subspace, because I mean, do you randomly pick the projection from the free group on two elements to?
No.
Or,
I said that a deterministic normal subgroup.
so this
Just
is
a black box. This is the black box.
Oh, so this is the point mass even, you're saying?
Exactly. That's the point mass that always outputs the same, like this always outputs the same normal subgroup.
Yeah.
So I'm just saying this lives here.
Is not.
That's the exercise. It's not a very hard exercise, but it is also not obvious. It shouldn't be obvious to you why it's there. You need to do something, but it's not a hard something. Okay. So, whose battery is low? Okay, great. So we have this picture. We have the closure of all the finitely described IRSs. We just call them the cosophic IRSs. And we have all IRSs. And Aldous and Lyons just asked, is this an equal sign? Okay, that's the question. And I'll say three things about this question in a moment, but our answer is no. So that's the whole talk. You can go. So that was their conjecture, and we showed that the answer is no. You will see that in a moment. It's not that easy. Like you need to do some things. We actually don't know if it's that easy. It's similar to other situation in math. The first proof is not that easy, so our proof is not that straightforward. But maybe someday someone will give a much easier proof. And there should be like 3 people in the audience. Okay? Yeah, you have a question? Or?
Just a quick question. How does, before like Hans's true and false? How is this related to cons, or is not really
It's
comparable?
closely related to cons, and I'll explain maybe later, but I essentially, like I gave a talk at the Institute for Advanced Study about this, and there I did it the other way around. I like explained very well what is this conjecture, explained very well what is the cons embedding problem, show that they are very closely related to one another, and then it's much easier to see that probably MIP star style approaches should help.
Okay.
Here I'm kind of hiding it under the rug. I just gave you this definition of what is the Aldous-Lyons conjecture. And I won't talk too much about the cons embedding problem, but if I'll have time and if you want to chat about it, I'll say more. But at this point, you shouldn't know. I didn't say the cons embedding problem. You shouldn't know how is it related to anything else.
Okay.
That's okay. But there should be 3 people in the audience still. Okay, so the first kind of person is just, okay, that's a nice question. Let's hear this dude until the end. Great, you're with me. Second kind of person is not well motivated. So let me in the next slide kind of at least motivate why you should care about this problem. And I claim that you should care. It is an important kind of problem. And the third person in the audience should ask themselves, how the hell is this the Aldous-Lyons conjecture? So usually the Aldous-Lyons conjecture is formulated completely differently. It asks, I'll write it on the board, well, every RO unimodular random rooted graphs, the Benjamin-Schramm limits of finite ones. So that's the original Aldous-Lyons conjecture. Do I have something to erase? I'll just work out with this piece. Okay, so I'll just say that there is a dictionary that relates this formulation. So if you heard of the Aldous-Lyons conjecture before, probably you heard of it in this formulation. And there is just a dictionary between this formulation and my formulation. So you can check that finite, okay, maybe subgroups. We already saw that subgroups of the free group are associated with Schreier graphs, right? So somehow choosing a subgroup is choosing a graph. And at least for the free group, and that's important, choosing a graph, at least if it's labeled correctly, is the same thing as choosing a subgroup. Okay. And then if the finely described IRSs, we just define them using the finite coverings, right? So finely described IRSs are almost by definition defined by finite graphs. And the third part of the dictionary, if you do want to move from this picture to the more graphical, the graph theoretical notions, you need to relate what are general IRSs. And it turns out that I didn't say what is a unimodular random rooted graph, but IRSs are exactly the picture on the other side of these unimodular random rooted graphs. And this is a theorem, okay, of Abert, Glasner, and Virag. So that's not that obvious, but it is part of like the first paper that actually introduced these IRSs already showed this dictionary. Okay, okay, great. So I handled these 3 people. And now maybe you didn't notice, but I called this closure, this weak star closure of the finely described IRSs, I just called them the co-sophic IRSs. Now, those of you who heard about some group theoretic problems, maybe heard of a sophic group. So let me just define to you what is a sophic group. In the beginning of the talk, I just told you that any finitely generated group is just the quotient of the free group, right? So you always can just find an onto homomorphism from the free group to this group. And you can find the normal subgroup here, right? It's just the kernel of this map. Everything that is sent to 1 here is in this normal subgroup. And I just call this group sophic. This group is called sophic if and only if the this Dirac measure, the point measure on this normal subgroup is in this weak star closure. So this IRS is co-sophic if and only if this group is sophic. And that's why the word co-sophic, right? Like it's the, I don't know, on the other side of the sophic thing is the co-sophic thing. I don't know. That's an intuition for that. And I will just say, and that's my motivation, there are many problems in math which fall under the following like situation, okay? So there are the set of all objects. For example, just think of all groups. So the set of all groups, and the set of the approximated objects. And I'm not explaining why this is called an approximated object, but the Sophic groups, those that I defined just a moment ago, just think of them as the approximated objects. Okay, so I have the Sophic groups, I have all groups, and there are many conjectures that are completely open. Okay, so Kaplansky's direct finiteness conjecture, Gottschall conjecture, some, like I can give a longer list, but I won't, okay? For example, that we don't know whether they are true for all groups, but they are known to be true for Sophic groups. Say you're trying to study the Gottschall conjecture, and you don't think the Gottschall conjecture is true. You think it's a false conjecture. You need to start somewhere. How would you start? You will start with something that potentially refutes the Gottschall conjecture. What is the problem? We don't know how to pinpoint even a single non-Sophic group. We don't know how to touch this region. We believe this region exists. We believe not all groups are Sophic, but we're not able to show that any specific group is not a Sophic group. And that just shows you our ignorance, okay? Like, that shows you that in some sense, our machinery is not good enough to touch these kinds of things. Now, if you replace all objects here instead of groups looking at IRSs, and instead of Sophic groups looking at co-Sophic IRSs, we finally gave an example that lives here.
Is it an explicit example or?
Okay, no, that's not an explicit example. That's just, it's similar to the Conze-Beddick thing where you define some combinatorial object and somehow the thing, like, it's like defining a functional and the optimum versus the functional is the thing that you show actually lives outside, but you can only construct explicitly the functional, not the object itself. Okay, that's like the how it works. But we know some things about it. We actually hope that maybe like we understand enough about the object itself, just using the functional to maybe refute other conjectures used. That's a good question, actually. Okay, so that's my motivation. That's the only motivation I'm going to give you, that this is a kind of problem that appears again and again in math, and or maybe not again and again, but there are at least a few cases of this kind of picture, and just giving methods that give you something that lives here and not here is very interesting and important. Now I'll move to the computer science. Okay, so up until now it was very mathy. It was the Aldous-Lyons conjecture. Let me do just switch gears and do very basic computer science. So remember 0, 1 star is just a free monoid over 0, 1. It's just all bit strings. A subset of bit strings is a language, and every language defines a decision problem, right? Like if I give you an instance, you just need to decide whether this instance is in the language. And we never think of the bit strings themselves, right? Like we usually think of the bit strings as encoding some combinatorial object, and the language is just asking about some property of the combinatorial object. So for example, given a graph, and here I'm not actually giving you the graph, I, for example, give you the adjacency matrix of the graph, and let's assume it's a simple graph, so it's only zeros and ones in the adjacency matrix. Is it 3-colorable? That's like a kind of question that you can ask. Out of all adjacency matrices of simple graphs, which ones are the 3-colorable ones? Similar thing you can do, you can just take a Python program, translate it using ASCII to a bit string, and then you can ask, okay, is this bit string encoding a Python program that halts when I run it? It's another kind of question I can ask. And a third kind of question, which is more like for the group theorists, if I have a finitely presented group, is it trivial? What does it mean? So I wrote you the generators of the group. I give you some relations, and in addition to the annihilation relations, I give you some potentially other relations. I just ask you, is there any non-trivial element in this group? Okay. And quite famously, this problem is NP complete, right? And these problems are two are RE complete. Okay, so this is the halting problem. This turns out to be equivalent to the halting problem, as hard as the halting problem. Okay, great. So this is just the usual setup of decision problems, but I need like what are called promise languages or gapped decision problems. Okay, and in the setup of a gapped problem, you have a set of combinatorial objects. Again, my blue notation is for the running example. So just think as graphs, for example. And then I give to each, instead of giving a yes/no answer for each object, I give you a value to each object. Okay, so for example, the value of a graph will be just the maximal proportion of edges, which is satisfied by a 3 coloring. Now, every graph, I can color all of it by the same color, and then this specific coloring gives me 0. But potentially, there are other colorings that give me higher and higher proportion of edges. And the 3 colorable graphs are exactly those with which value? By this definition? 1, exactly. Okay, 1 is all edges are okay, right? This is exactly being 3 colorable. So the objects that previously we asked about are the value 1 objects. Now I'm giving you some promise. Okay, so instead of distinguishing between objects with value 1 and value strictly smaller than 1, I give you some error theta. Okay, so I give you a gap theta, which is first of all, I choose it. So it's some strictly positive number. And I just tell you, I'm giving you the graph. Is its value 1 or its value strictly smaller than 1 minus theta? So for example, if I choose theta to be 0.01, this is the following kind of question. I'm giving you a graph, and I promise you, this graph is either 3 colorable, or at most 99% of its edges can be simultaneously satisfied by a coloring. Okay, so like it's a highly non-colorable, 3 colorable graph. That's the way you should think about it. So that's clearly a simpler question, right? If you know how to solve 3 coloring, clearly you can solve this one, because this is just, I guarantee you more about the input. But it's not clear whether this is as hard as 3 coloring, and kind of maybe one of the greatest achievements in, I don't know, complexity theory is actually this is as hard as the original problem, for at least some thetas. It's not true for all thetas. There are like trivial thetas. But for small enough thetas, it is as hard solving this blue problem as solving the original 3 coloring problem. This is a result of the PCP theorem. Any questions or remarks about that? No? Great. So this is my goal. Like I'm going in the, how much time do I have?
Like 20 minutes.
How much?
20 or
20 more minutes. Okay, great. I'll do even less, but don't worry. My goal now is to define to you a gapped problem. So I'm going to define a collection of combinatorial objects. Then I'm going to define a value for these combinatorial objects. This value would be between 0 and 1. And this will define for me a decision problem, a gap decision problem. Is this object has value 1 or value strictly smaller than 1 minus theta for the fixed theta that I will choose? So to define my combinatorial object would be the subgroup tests. So in my title of this talk, there was subgroup tests and the Aldous-Lyons conjecture. Finally, we got to the subgroup tests. These are combinatorial objects, but these are combinatorial objects that are inspired by subgroups of the free group. Okay, like they will be related to the first part of the talk. So what is a challenge? A challenge is a pair of a finite set from the free group. So I fixed a collection of generators. So S is prefixed before this definition. So a finite set K and a function from subsets of K. So 0, 1 to the K is just indicators of K. This is the same as a subset of K, right? So D is just a decision function. It takes a subset of K and gives me 0, 1. And you should think of 0 as a losing condition and 1 as a winning condition. So this will define some interactive proof protocol. So this is the challenge, just a finite set of words and the function from subsets of these words to 0, 1, win or lose. And I will say that a subgroup, okay? H is a subgroup. This subgroup wins against this challenge if and only if. So what can I do? I can just intersect H with K, as I did before when I defined the weak star topology. I will get a subset of K, right? And now I can evaluate D on subsets of K. it will be win when this is the winning condition, when the output is 1, and it would be lose when this condition is 0. Okay, so we understand what does it mean for a subgroup to win a challenge. What is a subgroup test? That's just a finite distribution over challenges. Okay, so I give you finitely many challenges, and I give you some probability distribution over the indices of these challenges. This is a subgroup test. Okay, so we understand now what a subgroup test is. Any questions about that? Great. So I just said beforehand, you should think of it as an interactive proof system. How? So you have a verifier, and the verifier wants to run the subgroup test. How does the verifier runs the subgroup test? So it has access to the mu, to the distributions over challenges. That's part of the definition of a subgroup test. It doesn't have access to an IRS. So this thing is generated by a prover, but you should think about it as a PCP protocol. So you get a black box function, okay, as like from approvers, from like an outside entity, and then you run some interaction with this black box function. So this is very similar here. You get this IRS from approver, from some outside entity, and then you can run your test. Why? You have two black boxes. One of them outputs subgroups. One of them outputs indices of challenges. You just push both of them. You get as an output an index and a subgroup, and you can just run the ith challenge over the subgroup that you got, right? We said that you can just evaluate the decision predicate, the ith decision predicate of this specific subgroup intersected with this finite set of words implied by the ith challenge. And this is either a 0 or a 1. So we see again, this will all, like the verifier either accepts or reject whatever I got. And you can see that this defines you a value. What would be the value? The probability that this specific IRS will make this thing being 1. So this is a pair. It's not only the value of the subgroup test, it's the value of the subgroup test versus a specific IRS pi. Okay, and that's just the formula for the probability that this will be 1, that this interaction will give you 1. And just note that this is continuous functional. From where to where? From the IRSs to the numbers between 0 and 1. Okay, so it's not really from the IRSs. You need to extend it to the vector space in which it lives, and then it goes to R, but it is a continuous functional from the appropriate spaces. Great, but this is not the value that we seek. Yeah.
Right, just maybe to make sure I understood the definition.
Yeah, of course, that's important
Are
stuff.
you using here the fact that it's an invariant random subgroup, or just the fact that it's a random subgroup?
At this point, no. Like
Yeah.
here, I just use the fact that it's a black box. You can think of your subgroup test as playing against other random subgroups, right? That are not invariant. And actually, it's important. It's similar to. This is very similar to the NPA hierarchy, like in quantum information theory. Like when you want to approximate the quantum commuting value from above, you actually relax. You define a relaxation of what does it mean to be a quantum commuting strategy. You can call it a local quantum commuting strategy. This would be like here saying, okay, I'm giving you a probability distribution, which is not an IRS, but it is like a local IRS, let's call it. And you extend the locality, and that's how you approximate like what you care. And we actually have like this kind of theorem coming soon. But yeah, as this definition, you can have just any probability distribution. Actually, any probability distribution on subsets, right?
Sure.
Also the subgroup, this can run against subsets. Other remarks? Okay, great. But my point is that this is not the value of the subgroup test. This is the value of the subgroup test versus a specific IRS. This is very similar to not what is the maximal proportion of edges that can be satisfied by 3 coloring, but what is the number of edges satisfied by a specific 3 coloring, right? So now I need to take a supremum or a maximum, depends on what I define it over. And there are 2 natural things to do, okay? So recall we had 2 sets. We had all IRSs, and we had the finitely described IRSs. And the strategies, you can think of the IRSs are essentially the strategy of the prover, right? So let's just think of the IRSs as strategies. I can take the supremum over all possible strategies, over all possible IRSs. and I can take the supremum only over the finely described IRSs. So the first one we will call the ergodic value of the test. That's just the name. So the ergodic value of the test is just the supremum over all values when I run over all possible IRSs. And the Sophic value of the test is the same thing, but I allow you only to use the finely described IRSs. So because this is a subset of this, and I'm taking supremum, a priori this is greater or equal to this, right? But what does the Aldous-Lyons conjecture say? It said that the closure of this set is everything. And I just said that everything here is continuous functional, right? So taking the supremum over a dense set is the same as taking the supremum over everything. So if the Aldous-Lyons conjecture is true, these two things are always equal. So now at least we already see a way of tackling the Aldous-Lyons conjecture. Give me a subgroup test for which these values are different from one another. Okay, that would be a way of refuting the Aldous-Lyons conjecture. But we will do it a bit like this. We will show some undecidability result that will imply that there exists such a separating subgroup test. Okay, but notice that we already now have actually two decision problems, right? I can ask you, okay, given a subgroup test, distinguish between ergodic value 1 and ergodic value strictly smaller than 1 minus theta. But I also have a decision problem regarding the Sophic value of the test. So which should I choose? You can choose both, but we chose the second one. Okay, just because the finite thing is very similar to finite dimensional quantum strategies, and we will see in a moment the relation. Okay. So my decision problem, I call it soft val theta. So for every theta, you can define this decision problem. Given a subgroup test, is it Sophic value 1 or is it Sophic value strictly smaller than 1 minus theta? Great. Now let me state two theorems. So the first theorem is that if the Aldous-Lyons conjecture is true, then no matter what the theta that you chose, soft value theta is decidable. And we actually construct an algorithm that no matter what, okay, you give this algorithm the theta, okay, it's actually a sequence of algorithms, right? For every theta, we define an algorithm. And given this theta, it will decide for sure whether a subgroup test is of value 1 or value strictly smaller than 1 minus theta, given that the promise is you're in either of these cases. Yeah. So that's like this first theorem. And the next slide is about this theorem. Yes, question.
In a very naive sense, should I think of this as a search from below or a search from above?
So you will see that it's a search from both sides. And because the Aldous-Lyons conjecture implies that finding that two values are equal, I have a search from above, a search from below, and because they are equal, it will find the correct thing. We will see it in the next slide.
Okay.
Yeah. So this is a conditional result. If the Aldous-Lyons conjecture is true, then this is decidable. The second theorem says essentially that this is undecidable. Okay, so let me just say it concretely. For every Turing machine M, and every, okay, so I'm giving only M, and I'm going to give you as an output two things. Both a subgroup test, just the description of a subgroup test, and the parameter theta, okay? And actually, this can be computed in polynomial time. That's not important for us, but I'm just saying our method gives you even like polynomial time calculation of these two things. So this must be a rational number, right? Because I actually can compute it. I can actually write it down such that two things holds. If the original Turing machine halts, the Sophic value of this test is 1. So here theta doesn't play a role, just if the Turing machine halts, this is value 1. But if the Turing machine never halts, the Sophic value is strictly smaller than 1 minus this specific theta. This shows you that if this was decidable, I can distinguish between the halting problem and, right, because I can calculate theta m, I can run the algorithm from theorem 1, I can decide the halting problem, which means, as a corollary, that the Aldous-Lyons conjecture is false. So that's the structure of her proof. Great. And now I'll say something about theorem 1, and then I'll kind of mumble things about theorem 2 and relate them to non-local games, and then we will go home. So how does our proof of theorem 1 works? We actually just show that there is an algorithm that approximates from below the Sophic value and from above the ergodic value, okay? And this is naive. Like there are only countably many finitely described IRSs, right? So just enumerate them, run them one by one, take the supremum, the maximum over whatever you saw up until now, and you will get a better and better approximation of the Sophic value from below. For the above approximation, we actually construct a sequence of linear programs that exactly use like some relaxations of invariant random subgroups that gives you smaller and smaller values, and in the limit, they will give you the ergodic value of the subgroup test. So that is the picture that we actually prove. But recall that the Aldous-Lyons conjecture being true means that this is the same line. So you have an algorithm that gets as close as you like to the line from below. You have an algorithm that gets as close as you like to the line from above, sorry. So for every like I gave you theta beforehand, that's very important. You can just halt whenever this distance is smaller than, for example, theta over 2 or something. And then for sure, you're either smaller than 1 or larger than 1 minus theta, right? So this shows you just the fact that I have this purple, so this blue line is like naive. This is slightly more involved, but still not that hard. And this is what we get out of it. Okay. Now let's, any questions about this? Like I kind of, oops. Okay. Any questions about that? Like, no, right? It's very clear what happens here, at least heuristically. Let me say something about our theorem too. So again, I would like to write something on the board. Can I fetch your?
Yeah, sure.
Yeah, that would be perfect. So as I kind of said along this talk, so probably some of you or many of you know about non-local games, and this is an analog of a result that already appeared in non-local games in some sense. So what happened in non-local games? So I'll just write non-local games. This is a set of combinatorial objects, okay? Very similar to subgroup tests. If you know them, you know them. If you don't, you don't, but it doesn't matter. It's just a set of combinatorial objects, and you can associate values to them. So here, the kind of value that we associate to them is called the quantum value. And the question that you ask about these combinatorial objects is the quantum value 1 or strictly smaller than 1? Then 1/2, okay, for example. Like let's theta give it the value 1/2. And this was shown, so you can associate, there is a function which is called the quantum value, val star usually, of a non-local game. You get a number between 0 and 1. And this decision problem, so this is by G, Natarajan, maybe I won't write their whole names. So G, Natarajan, Vidic, Wright, Yuan in 2019, they showed that the associate decision problem here is undecidable. So it is as hard, if I give you a non-local game, again, it's just a description, a combinatorial object, I just give you the description. Deciding whether its value is 1 or strictly smaller than 1/2 is as hard as the halting problem. That we already had, that's the big breakthrough that we actually we got inspired from, and we actually follow their techniques also. What we did, and this is this theorem, we took a subclass of these non-local games. So in these non-local games, there is a subset which we call tailored non-local games. And we generated a value-preserving map from this set to subgroup tests. So if the value here is 1, the subgroup test that I get has value 1. if the tailored non-local game has value strictly smaller than 1/2, then the subgroup test has a slightly worse upper bound, but still something that I can compute and can work with. Okay, so this is this theorem. And I think in some sense, this is our major contribution. And I'll say something about the fact that although at least like on the level of ideas, was our most important idea. Recently, someone published a paper that actually bypasses this, which is very nice. Like, I think that was the epiphany that helped us resolve the problem, but someone showed that you can kind of bypass it, and I'll say something about his result in the end. Okay, so we have a value preserving map from here to here. On the level of computer science, this is just a reduction, right? This means that this is a harder problem than this. So if you can just prove the same thing as G, Nataraj, and Vidic-Wright and UN on this subclass, so I restricted, I didn't allow you to use all possible games, non-local games, I'm allowing you just to use this subclass. Can you still recover MIP star is equal to RE? Okay, can you still show that this is undecidable? And that's exactly what we've done, okay? So that's our second theorem. We essentially reproved MIP star is equal to RE, this result, to this subclass. And most of the things work okay. Like if you know the MIP star is equal to RE paper, there are like 3 major parts, and they're how do you call it? Like transformation. Like they take a non-local game, they transform it to a new non-local game. This is called compression, and compression is composed of 3 parts. And we needed to change essentially only one of them. Like we had a very good luck. 2 of their processes don't kill the tailored condition. Like you stay in the tailored thing in a well manner. The only problematic part is the mid part, the PCP part, and we actually needed to define a different kind of probabilistically checkable proof. Like we needed to swap the probabilistic checkable proof in their paper by something more complicated, essentially. But somehow that was enough to reprove their result for this subclass. And that's it. That finishes the proof, right? Because now that this is undecidable and this is a harder problem, this is undecidable, and we're done. Thank you for coming.